All right. Hello, everyone. Welcome to the Multi-Agent Learning Seminar. Today, we're really excited to have Sriram with us. Sriram is a postdoctoral fellow at Vector Institute, Toronto. Previous to this, he completed his PhD in the Department of Electrical Engineering and Computer Engineering at the University of Waterloo. His primary research interest is in the area of multi-agent systems. Particularly, he's interested in the issues of scale, non-stationarity, communication, and sample complexity in multi-agent learning systems. His long-term research vision is to make multi-agent learning algorithms applicable to a variety of large-scale, real-world problems, and to bridge the widening gap between theoretical understanding and empirical advances of multi-agent reinforcement learning. Sriram has been a recipient of several prestigious fellowships, such as the MITAX Global Link Research Award, the MITAX Graduate Fellowship, Pasupalak Fellowship in AI, and Vector Postgraduate Research Award. With that, welcome Sriram, and thank you for joining us, and I hand it over to you.
Thank you, Rupali. So yes, let me get started. So like I mentioned before, please feel free to interrupt me with questions. You could raise your hands or just unmute and ask. And you could also give me feedback about the pace of my talk as I go on. Like if I'm going too slow, and if you feel like you just don't know these things and I have to just quicken up, then just let me know. Or if you feel like you're just lost, I'm going too fast, you can just unmute yourself and say, "Hey Sriram, slide number 20, you lost me in slide number 5, right?" So I'm going to be very welcoming of that. So again, good morning, good afternoon, good evening, whichever part of the world you're in. I am Sriram, as Rupali introduced. I'm going to talk about accelerating training and multi-agent reinforced learning through action advising. Before I start, let me give a shout out to my awesome collaborators, Matthew E. Taylor. Matthew E. Taylor is Associate Professor at the University of Alberta and Alberta Mission Intelligence Institute. Kate Larson is a professor at the University of Waterloo, and Mark Crowley is an associate professor at the University of Waterloo. Yeah, so let me get started. Okay, so we know that multi-agent reinforcement learning has had a lot of successes in the past decade or so. I don't have to convince this audience that multi-agent reinforcement learning is awesome. So we have started with we went from single simple grid world type environments to more complex games like Dota 2, chess, AlphaGo, and now we have started seeing more applications of multi-agent reinforcement learning in the real-world environments, in robotic operations, stock trading, and other such things. But if we just take note of the kind of domains where we have been successful so far, all of these domains, or at least most of these domains, can be classified to having these 3 properties. So all of these domains have simulators that can provide us potentially infinite data. And typically the size of the environments that we have been dealing with has been small, where we handled about 2 to 10 agents. And all of these domains require algorithms, like the algorithms that learn very good policies in these domains require very large amount of compute. So to provide some example of that, OpenAI 5, which provides superhuman performance in the game of Dota 2, requires 180 years of gameplay data each day with a massive compute infrastructure that has 256 GPUs and 128,000 CPU cores. And AlphaGo is trained on 10 to the power 7 games, taking over a month of training. So if the name of your company starts with F, A, N, or G, then probably you have all of these infrastructures, and it is possible for you to do this training. But if you belong in academia like me, or if you are in other small or medium-sized companies, then you don't have such amounts of infrastructure lying around to train multi-agent reinforced learning algorithms. And typically, when we go to the industry and talk about our successes, industry generally does not care about Go or chess or Dota, right? So what I'm actually interested in is the kind of domains that you can see in this slide. So I'm interested in looking at multi-agent reinforced learning applicability in domains like wildfire fighting, ride sharing, pandemic response, or autonomous driving. So these are all like real world domains and actually kind of open world domains where there are lots of agents, typically millions of agents, and there is a relative paucity of data available in these domains. So it's not possible, or it's generally intractable to come up with simulators that can simulate the entire domain in some of these elements. So it is there is always a relative paucity of data when you're talking about these domains, and the kind of organization that deal with these problems have a limited computational infrastructure. So we don't have infinite compute as well. So now my objective is to try and make multi-agent reinforced learning algorithms applicable in the kind of domains that we see here. But before I go into that, let me probably show you this basic multi-agent reinforced learning slide that everyone should have. And I'm sure all of you have seen this before. And if you've not seen this before, probably you're in the wrong talk. So let me just not take too much time here. But what I want to mention is that multi-agent reinforced learning is important because in the vast majority of cases, like reinforcement learning, about 95% of reinforcement learning literature out there is in the single agent context. But it's only very rarely the case that it's only your one agent that has agency and everything is part of the environment. So yeah, maybe I'm preaching to the choir here, but multi-agent reinforced learning is an important research area, and I'm happy to see that there is a lot of interest in this area in the last, say, a decade or so. So my objective is to, like I said, my objective is to make multi-agent reinforced learning applicable in a lot of real-world domains. And one important impediment to that objective is the problem of sample efficiency. Right? So agents actually are trying to learn from scratch. And when they try to learn from scratch, the learning is extremely slow and inadequate. In this talk, I want to really motivate the idea that learning from scratch is for losers. Okay, so we just don't want to learn from scratch in the vast majority of cases. But unfortunately, if you look at literature, so I was at AMAS this year, where almost every single paper that was presented was learning from scratch. So as a community, I think we should start discussing about some alternatives to the kind of default learning from scratch idea that we have so far. Agents typically need help at the beginning of learning. So at the beginning of learning, agents have a policy that is next to random, right? It's actually pretty useless. So it is during this time that we have to try to think of ways of handholding the agent and try to provide some way of accelerating training and some help in choosing better actions. And one important observation here is that in all of these real-world environments that I showed before, there are some existing solutions or models that can be leveraged. So in all of these situations, for example, in wildfire fighting, we have a series of scientific physics-based models called physics-based simulators, which are available and which are being used in practice. Now, each of these available solutions are suboptimal because the problem is actually complex. So it's very hard to come up with optimal solutions in these cases, but still we have something. In most of these real-world environments, we have something that works, right? So the motivation here is to try and leverage these existing solutions and models and try and accelerate the training of multi-agent reinforcement learning algorithms. So to achieve this objective, we use a very general framework for multi-agent action advising and multi-agent reinforcement learning. So we are going to use the term advisors to mean some general framework of an external source of knowledge that is available for the agent to leverage. So agents have some, we assume that agents have access to some external source of knowledge, and this could be any source of knowledge. It could be a human, it could be pre-trained models, or it could be physics-based models like I just mentioned, and so on. And we broadly call all of these external source of knowledge as advisors for the purpose of this talk. So we are going to introduce a principal framework for multi-agent reinforcement learning to leverage these set of advisors. And I will show that this principal framework will be very general. So we will not have restrictive assumptions on the advisor or the type of environment in our work. And we will introduce some practical algorithms to learn from the advisor and some practical algorithms to evaluate the advisor as well. We will also show that all of our methods are theoretically principled, and we'll have some theoretical guarantees that we will discuss maybe under some restrictive assumption, but we will also provide some theoretical guarantees as well. So this is the outline for today. Right. So before I go forward, let me briefly mention certain areas of literature that will be relevant for us. So when I started my PhD, I was looking into the kind of problems I mentioned before. I was very interested in using reinforced learning and by extension multi-agent reinforced learning for for problems like wildfire fighting or autonomous driving and so on. And when I was looking for solutions for these kind of problems, I came across a bunch of literature in multi-agent reinforcement learning and reinforcement learning, which was doing learning from pre-existing knowledge, and I was really excited by that. So the introduction of papers generally say that, you know, we have this great method that can learn from pre-existing knowledge, so we can accelerate training, we can be sample efficient and so on. And this is really exciting. I'm excited by it. And when I keep reading the paper and I go to the settings and I actually read the setting at which they apply this particular problem, they have a very restrictive problem setting. So they kind of have some restrictive assumptions on the type of environment or on the nature of the advisor or on the number of agents. So either it's just 2 agents or these are like algorithms that will only work in small discrete state and action spaces, or these are algorithms that only work for games which are fully cooperative, fully competitive, or the advisor or the demonstrator that you use has to be an expert. So this demonstrator or advisor cannot give any wrong demonstration or advice anywhere in the environment. And if they happen to do that, then we cannot learn anymore. So these kind of assumptions, restrictions make the current set of literature inapplicable to the kind of problems that I care about. And I'm going to try and summarize some of these points in the next 2 to 3 slides. So the two most important areas of literature that is relevant to me are imitation learning and learning from demonstrations. So within the area of imitation learning, there are 2, again, sub fields of research. One is behavior cloning, the other is inverse reinforcement learning. So behavior cloning is a type of method where there are some advisor demonstrations, and this advisor, which is providing the demonstrations, is assumed to be an expert. So the advisor is assumed to be fully optimal or at least near optimal. And whatever demonstrations the advisor is providing, the agent is trying to just mimic the advisor using some kind of a supervised learning approach, right? And this has been successful in certain contexts, but it's been in a vast majority of situations in the multi-agent context, this has been really more or less a failure. This method has not been successful, and the assumption of near optimal or optimal expert makes this idea less applicable in the real world environments, because it's very hard to come up with optimal solutions in some of the environments I was talking about, like wildfire fighting. And further, behavior cloning has its own issues like distribution drift and high variance, which makes its applicability limited. The other field of imitation learning is inverse reinforcement learning. And here the objective is to learn a reward function from an expert again. So again, the common assumption is that this demonstrator is an expert and they are going to be optimal or at least near optimal. So we do have that assumption. And also, when inverse reinforcement learning has been used in the multi-agent context, we generally see these type of restrictive settings that I had just mentioned previously. So this is one class of methods. The other class of methods has been like the learning from demonstration literature. So I hope that most of you would be familiar with algorithms like DQFT, NAC. DQFT is DQ learning from demonstrations. So the common approach in the learning from demonstrations work is to do a pre-training, which means that you have a demonstrator which demonstrates all of the data before the actual training starts. And we have a neural network that does a set of pre-training on this offline data. And whatever the agent is pre-trained before the actual training starts, and when the actual training starts, you just freeze all the weights after the pre-training, and then you use the neural network that was pre-trained for the actual training. So that is the general idea. And in this case, from the learning from demonstration literatures, we allow suboptimal advising. So we don't need optimal experts as in the case of learning from, as in the case of imitation learning. But the problem is all of these different methods, DQFT, NAC, most of these different methods have only been tried in the single agent setting. So even though there has been some effort in trying to use these in the multi-agent setting, the performances have been really underwhelming. And the major problem has been this idea of training, where you just assume that you have this demonstrator who demonstrates everything before a game starts. And now let's say that you have learned all of this information before the game starts. And when you start playing, you have this inherent non-stationarity in the game where you have an opponent and the opponent does something completely surprising. And whatever you have learned previously is just next to useless now, because you cannot predict what an opponent will come up with during gameplay. So because of these reasons and because of the non-stationarity associated with the multi-agent environments, the performance of the classic learning from demonstration type algorithms have been underwhelming in the multi-agent literature. And so there have been some cases where they have been successful. And in these cases, you again find these restrictions on the setting and on the demonstrator, which I mentioned in the previous slide. And there is also another class of work that is relevant to me. And this is learning from limited human demonstrations. And there are two algorithms here, HAT, which is human agent transfer, and CHAT, confidence-based human agent transfer. I'm not sure how many of you are familiar with this class of literature. So here the idea is that you have a human who provides some limited demonstrations to an agent. And this happens offline, similar to the learning from demonstrations work. This happens offline, and the agent learns a classifier based on the human demonstrations. And this classifier is available online, and this classifier is used to advise actions the agent when the agent is making some decisions. And to the best of my knowledge, all of these algorithms have mostly been studied only in the single agent context. And this type of work does allow suboptimal advising, so that is good. But there is a very important assumption on consistency, which is hard to justify in the multi-agent context. To provide more information on that, if, for example, the CHAT algorithm, confidence-based human agent transfer, so this algorithm builds a classifier, and this classifier provides a prediction of an action that an agent has to perform at every state. Now, this prediction, if prediction changes from one time step to the other for the same state. So let's say that you are in some state at a particular time step 10, and let's say that the classifier suggests an action to go right. Okay, and if you come back to the same state at time step 100, and if the same classifier suggests you to take action left, then you will reduce the confidence on the classifier. So the classifier, and so you just think that you have a classifier which is not really sure of itself. Sometimes it tells you to go left, and sometimes it tells you to go right. So maybe the classifier is just providing some random advice, and therefore let's not trust it enough. Right? But in the case of multi-agent learning, this is going to be something that is important, and this is going to be something that is expected of an advisor, because you know that you are in this non-stationary environment with a non-stationary operand, and the operand can be, the operand can be learning and mixing its strategies, and you must also be mixing your strategies to be able to provide best responses. But this work was developed in the single agent context, where you will simply reduce the confidence on a classifier if the classifier provides different advices based on the same state, based on the time you reach that particular state. Right? So that is something that is limiting in the multi-agent context. And again, also using offline demonstrations. Yes, is there a question? No? Okay.
No, I'm just trying to share some resources for hat and chat, although I'm not sure if they're correct.
Okay, fine. That's fine. Okay, so now let me just formalize whatever I've said so far. The intuition here is that humans very seldom learn from scratch. So humans are not losers. So humans don't learn from scratch. But whenever we do training in the multi-agent or the single-agent context, most of the time, 99% of the literature out there learns from scratch. And this is something that we want to change. And this is something that we want to push against. And let me just summarize the limiting assumptions in the previous methods that actually do learn from pre-existing knowledge. So the assumptions are that the demonstrations come from some offline source, or we require some fully optimal experts, or there are some restrictions on the multi-agent environment itself, or there is this fourth assumption that all demonstrations are just coming from a single demonstrator. So which means that whatever demonstrations you get, whoever is demonstrating it and all the demonstrations that you get, there are no conflicting demonstrations, which means that if you have two advisors who are giving who know different things and who have different opinions about a particular state, then they will just give you conflicting information. Right? And if there is, if you just assume that everything just comes from the same source, then you don't have this problem. You don't have any conflicting information. But in practice, for the kind of environments that I talked about, especially something like firefighting, we have like a series of physics-based models, where some models are good for say predicting the weather, and some other models are good for the vegetation type and so on. And it's typically the particular agent that has to learn from this diverse set of sources has to be able to assimilate different information and learn from conflicting advice. But most of the previous work assumed that there's no conflicting advice, and that is another assumption that previous methods have. And most of these assumptions are because of recycling single agent algorithms. So when people start working on learning from advising in the multi-agent context, people generally start from algorithms that have been extremely successful in the single agent context, and they try to somehow recycle those methods for the multi-agent context. But we have a set of negative results that show that this is not useful, and this method has not been successful. So we have to start thinking about building algorithms only for the building algorithms more customized towards the multi-agent context, and that is what I'm going to talk about today. Okay. So in this talk, I'm going to talk about two particular publications that I have with my co-authors. One is Multi-Agent Advisor Q-Learning, which was published in Journal of Artificial Intelligence Research last year. And this introduces a principal method for learning from a single online advisor. So in this context, from all the four assumptions that I had listed in the previous slide, I relaxed the first three assumptions and I retained the fourth assumption. I retained the assumption about no conflict demonstrations, but I relaxed the other three assumptions. And subsequently, this year at MARL, we have a paper, Learning from Multiple Independent Advisors in Multi-Agent Reinforced Learning, that relaxes the fourth assumption as well. That introduces a principal method that can also learn from, conflicting advisors. Okay, so I'm going to talk about both of these works in the next 30 minutes or so. Okay, so any questions to this slide? Okay, that's good. Okay, so let me start with the first publication or the first set of work on multi-agent advisor Q-Learning. Here, now we will assume that there is just a single available advisor. So there is no question of conflict demonstration. So we retain the fourth assumption, like I said, there is going to be no conflict demonstrations. And we are going to make the advisor available online for model training. So we have a set of agents which are trying to play in this multi-agent environment, and each agent knows that it's in this non-stationary environment, and each agent will have an advisor that it can get some advice from. So the number of advisors for each agent will be at most one. So an agent can or cannot have an advisor, but they can not have more than one advisor. So that is the setting. And in this setting, we relax the first three assumptions. Like I said, we use the term advisors because these advisors can be suboptimal. We have no assumptions about them being optimal. And we don't have any assumptions on the optimality of these advisors. And we will have some settings without any restrictions on the multi-agent environments itself. And we will have the advisors available online. So we relax the offline demonstrations assumption as well. Right. So, so we have, yes, so there is a question.
Yeah, sorry, so when you mean like online advisor, does that mean like an agent can like query this advisor? What does that mean? I understood offline advisor that we have like their demonstrations from before or something. So online means that you can query.
Exactly. So there is an advisor, you can just ask for advice at any point of time. So you can just, so you have a state, you can just, feed that state, like think of the advisor as a black box. You can just feed the state into the black box and you get an action recommendation. This is just oversimplification, but you can think of it as something like that.
Sounds good. Okay. Thank you.
So yeah, any other questions? Okay, so we are going to look at general sum stochastic games. So this could be, this is highly non-restrictive. This could be like mix. These are mixed settings, this work is applicable to cooperative games, competitive games, or mixed games, and so on. So therefore, we don't really have any type of restrictions on the environment, and no restrictions on the optimality of the environment as well. So here, the setting is designed in such a way that an agent has at most one advisor, and the agent can choose to use its policy to pick action or query the advisor to pick an action. So agent has the choice, and we assume free communication with the advisor, no communication otherwise. So there is no agent-agent communication, but there is free communication with the advisor. The agent can talk to the advisor free, its own advisor free. And here we will talk about two particular scenarios. One is about learning using the advisor, which means that the agent is tasked with learning an optimal policy, and the agent can leverage the advisor when it's trying to learn an optimal policy in the environment. The second scenario is about learning about the advisor. So if an agent is presented with the advisor, the agent may want to evaluate the advisor and learn how good this advisor is before using this advisor in a real environment for taking actions, right? So in this case, we provide another algorithm where the agent can actively query the advisor and just learn about the strengths and weaknesses of the advisor and how good the advisor is. And this also helps in choosing between advisors. So if an agent has 4-5 choices of advisors that it can use to learn from, it can use the second algorithm to pick one advisor and just stick to that advisor and then just ignore the others. Okay. So we come to the first scenario, which is admiral decision making. So I think I missed this one previously. So the framework that we use is called Advising Multiple Intelligent Reinforcement Agent Learning, or ADMIRAL. So that's the name of our framework. So in this context, we have two scenarios. The first is called Admiral Decision Making, or ADMIRAL-DM. The second is called Admiral Advisor Evaluation, or ADMIRAL-AE. Right, so we come to the first scenario, admiral decision making. So here the objective is to learn the best response, or learn like the optimal policy that the agent has come up with given the strategies of the opponent. And we have the architecture as provided in this particular figure here, where there are n agents where n is greater than or equal to 2, because we are in the multi-agent setting, and each agent gets a state from the environment and has to pick an action. So I'm now just considering the most basic setting where it's all fully observable, but our algorithms are applicable in the partially observable context as well. So let's assume that everything is fully observable. The agent gets the global state, and now the agent has to choose an action. In this case, the agent can query the advisor. The agent can use the advisor, query the advisor to get an action recommendation, and then perform that action. Or the agent can just rely on its own policy. So this is our setting, and we do the classic joint learning update where at every time the agent updates its own Q estimate using the joint Q function, where the Q function is parameterized by the state as well as the joint action of all the other agents. But whenever the agent is trying to pick an action, we introduce a technique called probabilistic policy reuse, PPR. This technique is popular in the stochastic approximation literature, and not so popular in RL, but in stochastic approximation literature. So we have an algorithm that will listen more to the advisor advisor in the early stages of training. So it's a switch that you control. And in the beginning of training, when the agent has no confidence on its own policy, or it's its own policy is just next to random, it will listen a lot to the advisor. And over time, as its own policy keeps improving, the agent will steadily reduce its dependence on the advisor in such a way that in the time limit, the agent is only going to depend on its own policy. So the agent will simply stop listening to the advisor. And there is exploration that happens here using epsilon greedy, and we have the greedy limit with infinite exploration guarantee that in the limit, the agent will just rely on its own policy. So this is useful because during training, you can make an agent rely on an advisor, but when the agent has to execute the policy in the real world, then you can just throw away the advisor and then make the agent just rely on its own policy and deploy it just as a single entity, right? So that is the first setting. We have another setting called Admiral Advisor Evaluation, ADMIRAL-AE. So here the objective is to evaluate the advisor. So it's not to, yeah, so there's a question.
Yeah, sorry. I have a question in the previous slide. So in the Q function calculation, I didn't quite understand where is the component of the advisor.
Yeah, so what happens is the advisor. Yeah, so when the advisor recommends an action, you end up performing the action and you update the Q estimate of that action. So it's not really reflected in the equation per se, but it's in the way you select actions. So this is like, you rely on the advisor to improve your performance, and also in a way kind of bias learning towards something that the advisor thinks is good in this particular context.
Okay, so, and then at the beginning of the training, we just take that action directly that the advisor recommended. And then later we do what? We rely on our own Q values?
Yeah. Yeah, so think of this as, so you rely more on, so at every point of time, the agent has this choice. The agent can rely on its own Q values to pick an action or listen to the advisor. But the algorithm is designed in such a way that the agent relies more on the advisor at the beginning of training, and the agent relies less on the advisor in the later parts of training, in such a way that it is guaranteed to only rely on its policy in the limit.
Gotcha. Cool, thank you.
Yeah. So that is the first setting. The second setting, Admiral Advisor Evaluation, is designed in such a way that an agent is now trying to evaluate an advisor to try and understand how good the advisor will be in different parts of the state space. So here, if you look at the architecture, we have only one advisor. So we assume that there is only one advisor in the system. Because the objective is to evaluate the advisor, it's not to learn an optimal policy. So we have an agent which is trying to evaluate the advisor, and the agent can simply clone itself into multiple agents and use the same advisor to pick an action and then see how the performance is. Or we actually provide different scenarios where the agent can actually simulate some baseline opponents and then rely on the advisor and see how the performance is against these baseline opponents. So all of this happens in a phase called pre-learning phase, and this is optional. So there is actually, if the advisor is available beforehand, it's useful to evaluate the advisor. And if the advisor is not available, then you can just skip this phase. So if the advisor is available, then there is a pre-learning phase where you simulate some opponents or just clone yourself into multiple agents and then follow the advisor and see how good the advisor is. So here again, we have a Q learning equation. We have a Q update where the Q values are updated based on the advisor's Q or the expected utility that the agent gets when following the advisor recommendations. So that is used to update its own Q values. And here we have an algorithm which is where the agent recursively updates its Q values. And then once the Q values converge or comes close to convergence, I will provide some convergence guarantees in a bit. The agent will then use the Q values to provide some useful information about the performance of the advisor, to know the strengths and weaknesses of the advisor. So we provide, in the paper, we provide some ways in which the evaluation can be used. And one important way in which it can be helpful is to determine a hyperparameter which which is like the hyperparameter that determines the amount of times an agent will listen to the advisor in probabilistic policy reuse. So if I go back to the previous slide, here we are doing probabilistic policy reuse, where agent starts listening to the advisor for lots of times in the beginning, and then steadily reduces its dependence on the advisor. But in the beginning, if the agent has evaluated the advisor and knows how much to trust the advisor, then it can stick to a percentage of times with which it will listen to the advisor. So let's say that it has evaluated the advisor, and let's say that it has determined that an advisor is good in 80% of the states, state space, then the agent will only rely on the advisor 80% of the times, even in the beginning of training. The other 20% of the times, it will just depend on its own policy. Right, so this is one approach that we suggest, and we also have some other suggestions in the paper as to how the evaluation can be used to determine the strengths and weaknesses of an advisor before using it for learning. Right, so in this context, we are able to provide some theoretical guarantees under a set of common assumptions for general sum stochastic games. So if you have followed the literature on general sum stochastic games and theory in general sum stochastic games, you will know that we can only provide guarantees under a set of very strong assumptions. And we rely on such strong assumptions here, but we also actually evaluate those, we kind of qualify those assumptions and show that some of these assumptions that were used previously can be relaxed in certain ways. So in the first result we have is that we show that the Q values that follow ADMIRAL-DM converge to the Nash equilibrium. So this is the classic convergence guarantee we have in general stochastic games. So what we are seeing here is that even when you use external knowledge to bias learning, even if that external knowledge is suboptimal, your asymptotic performance will not be disturbed. In asymptotically, you will still reach the optimal performance, or you will still reach the fixed point that you're interested in. So here we reuse this assumption from Hu and Millman, which stated that the Nash equilibrium has to be a global optimum or a saddle point at every stage game in the stochastic game. And actually Hu and Millman's assumption has three assumptions rolled into it. So the first assumption is that the Nash equilibrium has to be a global optimum or a saddle point. The second assumption is that the same equilibrium point has to be used for every stage game. Like you cannot alternate between global optimum and saddle point. You have to use the same thing for every stage game. And the third statement is that you have to use this the expected utility at the equilibrium point to update the Q values. So actually, we show that you don't really require the third statement. As long as you have the first two statements, that is enough guarantee that such Q learning based algorithms converge. Yeah, so this is just an aside, but the important aspect of this result is that we show that the asymptotic performance will not be disturbed. And in the case of the ADMIRAL-AE, we show that the algorithm will converge to an epsilon equilibrium, where this deviation epsilon from the optimal point will depend on the nature of advisor, will depend on how good or bad the advisor is. So this is the set of theoretical results we have. And then subsequently, we show that this kind of Q updates that we are using, yes, you have a question.
Yeah.
Yes, Rupali.
If we can go back to the previous slide. So I don't have a whole lot of like game theory background, but I have a question around the equilibrium. So if we don't use ADMIRAL, let's just say ADMIRAL-DM, even then we would converge to the Nash equilibrium, would we, or would we not? Is ADMIRAL adding?
You have to make that question more precise. So what are you doing actually? How are you learning? So if you're just doing regular Q learning, then you will not converge to Nash equilibrium. But if you're but if there are certain special algorithms that will guarantee convergence. There is one algorithm called Nash Q learning, which Hu and Millman introduced, where you are using the expected utility at the Nash equilibrium to update the Q values. That will converge to the Nash equilibrium under some restrictive assumptions. Yeah.
Okay. Cool. Yeah.
Any other questions? Okay. Yeah, so then we have, I have the neural network implementation of ADMIRAL-DM written out in this slide, the pseudocode, the flowchart written out in this slide, where the idea is to use the advances introduced by me et al. In the DQN paper. So here we have, you're using neural networks as the function approximator, and then we are using two networks, the evaluation and the target network, and we are also using the replay buffer. So we are just introducing all of these techniques on top of the Q update that we have, and we're doing this both for ADMIRAL-DM as well as ADMIRAL-AE. Also, we have another algorithm, ADMIRAL-DM, actor critique, AFI, which is using an actor critique update. So the Q values are the critique, and the policy derived from Q will be an actor. So this makes it applicable to continuous action space environments, and also to centralized training, decentralized execution type environments, because when you're using the actor critique update, you only have to have a centralized assumption when you're updating Q values during training, and during execution, you can simply use the policies directly. So we have these three algorithms, which are function approximation-based implementations on the methods that we introduce. So in this context, we have some experimental performance in a series of test beds. So here I just have, I will show some results on three domains. Palmer-Man, which is 2 to 4 agent discrete action competitive environment, and Pursuit, which is an 8 agent discrete action cooperative environment, and Waterworld, 5 agent continuous action cooperative environment. So in the experimental I will describe the experimental details for Palmer-Man, and this is very similar for several other domains that we test as well. I will show you the results for two other domains. So initially, we have a pre-learning phase where we start with 4 advisors. So we assume that there are 4 advisors available in this setting, and these are 4 rule-based advisors, which is already present in Palmer. If you're familiar with Palmer-Man environment, you know that in Palmer-Man, there are some rule-based agents that are already present, and these are like the baselines that we try to outperform using reinforcement learning. So I designed some advisors based on those particular rule agents, and I designed the advisors in such a way that we have decreasing quality. So advisor 1 is better than advisor 2, which is better than 3 and 4, and so on, 3 and 4. And then I now use ADMIRAL-AE, the evaluation technique, determine which advisor is good out of this set of advisors, and also to check how much to rely on these advisors. The training happens for 50,000 episodes. So this is the first pre-learning phase. Subsequently, I have a training phase where once the pre-learning phase has happened, you pick an advisor, and advisor 1 is picked from the pre-learning phase. Now we have a series of baselines, DQN chat, DQFDs, these are like learning from demonstration type baselines. And then we have a head-on one-on-one contest between ADMIRAL-DM and ADMIRAL-AC. And the second phase uses advisors as well as exploration to learn. So the agent can rely on its own policy or listen to the advisor for choosing the best action in this phase. So, and the third phase is the execution phase, where the trained algorithms simply fight against each other for 10,000 episodes. There's no further training and no further influence of advisors. So this is like deploying the algorithm in the real world, and you have no more access to the advisors. So here I show some results for the pre-learning phase, where I have ADMIRAL-AE versus DQN. So the take-home message is that for the 4 advisors, the ADMIRAL-AE clearly shows advisor 1 being better than advisor 2, being better than 3 and 4 based on the performances. And if we use the previous formula that I introduced to determine how much to listen to an advisor, we get that we have to listen to advisor 1 with for 80% of the times, advisor 2 70% of the times, 3 40% of the times, advisor 4, which is very bad, just don't listen to it at all. You're simply better off listening to your own policy than listening to advisor 4. So that is what we get from the first phase. So then we go to the second phase, where we perform training and execution. And here we have ADMIRAL going head-on-head in Palmer-Man versus DQN, chat, and DQFD. And we show that ADMIRAL performs better than all of these baselines across both training as well as execution. So this shows that ADMIRAL is able to learn well from advisors, so it's able to accelerate its training. And also, once it has finished learning, it has no more no more dependence on the advisor, no more availability of the advisor, even then it's able to just use policy and provide better performances than other baselines, which cannot learn from advising or learn from offline advising in the case of DQFT. So we have results on Pursuit and Waterworld as well. We do a similar pre-learning, training, execution type experimentation. In training and execution results here for Pursuit, we show that across the baselines, ADMIRAL-DM provides the best performances across both training and execution. And similarly, in Waterworld, here this is a continuous action-based environment, so ADMIRAL-DM is not applicable. So we use ADMIRAL, the Autocracy variant of ADMIRAL, and we compare that against PPU and DDPG, and we show that against these classic continuous control algorithms, we get better performances. Yes, so there was a question.
Hey, Sriram, could you go to slide 25? So I think, just to clarify, the legends in the top middle and the bottom left, are those switched? It doesn't affect the results, I believe, in context.
Okay. Yeah.
Just for
actually, yeah. So there is an error
the people
here
that noticed.
Yeah.
Sorry.
So this is actually This is actually this one, and this is for this figure. And I'm sorry about the confusion. Yeah.
No problem. Thanks.
Yeah. Okay. Yeah. Any other questions? Yeah. Okay. Right. So now that completes the first set of slides. So I will, based on the amount of time available, I just briefly mention a couple of important things about the second paper. So this is learning from multiple independent advisors in multi-agent reinforcement learning. So the objective is that we are relaxing the fourth assumption. So I said we had 4 assumptions, but we'll retain the fourth assumption about no conflict demonstrations, and we relax the fourth assumption as well. So we have relaxed all the 4 assumptions. So in this setting, we will assume that there is more than one advisor. So if we go back to the motivating domains like wildfire fighting, we have a series of fire simulators that they can rely on, and some simulators are good for, say, the weather predictions. Other simulator is good for vegetation mapping and so on. And here we have a situation where each advisor is good at different parts of the state space. So you have a set of advisors. Each advisor is probably good at a different part of state space, and the objective for the agent is to pick which advisor is good at that particular state space and learn from that advisor and ignore the others. So we want to have an algorithm that combines the expertise of different advisors at different parts of the state space. So in this context, one particular prior work that I have to mention. So there was this work called two-level Q-learning, TLQL, from Lee et al., which was released in 2019. I think this is like a workshop paper where the two-level learning was introduced. And the idea was to maintain 2 Q tables, where the high-level table would learn the estimate of a state advisor pair. And the low-level Q table is just the classic Q table we know before learning, which will learn the value for a state action pair. So in the high-level Q table, there is like a series of advisors. Now you have more than one advisor available to the agent. And let me remark that this is only for the single agent setting. This is not for the multi-agent setting. So there is a single agent, and that agent has access to multiple advisors. And there is this Q-level, 2-level framework where the agent pick an advisor from the high queue, and then to pick an action in the low queue. And the agent can choose between following its own policy. You can see that the RL is also a part of the high queue table. So the agent can choose to follow its own policy by picking RL, or choose to follow an advisor. This is a choice that the agent has. So this was introduced by Lee et al., and then there was a synchronization step that was included in the update. So at every point of time, the agent will choose an advisor, pick an action from the advisor, execute the action, and do a Bellman update for the low Q table. So after making a Bellman update for the low Q table, this is just the classic Q learning Bellman update. After updating the estimates for the low Q table, there's a synchronization step where the agent simply copies over values from the low Q table to the high Q table. So if advisor 1 suggested action 3, then the Q value of action 3 will be the Q value of advisor 1. So that is the impression. So then, this is the first method. If I'm not wrong, this is the first method that introduced a multi-level learning to learn from multiple advisors simultaneously in reinforcement learning. But this was in single agent context. But this is the first method to do that. But there was, again, no assumptions in optimality, which is very good. And this showed some good empirical performances in some domains. Maybe I think in Atari games and some other Joom-like environments, it showed good performances. But this method was having some critical limitations. And the first limitation is that it's only for single agents. And when you try to use it for multi-agent, the method just fails. And the second limitation is that this method assumes that the advisors are available forever. So it's not like what we discussed before, where you can learn from the advisor and then just throw away the advisor and just use the agent for deployment. Here you require the advisors to be available forever, and you require all the advisors to be available forever. And this synchronization step is something that was that proved to be problematic empirically, because the intuition here is that, if I go back to this slide, the intuition here is that in the beginning of learning, the agent has a policy which is next to random. So it does not want to rely on its own RL policy. So it will rely on advisors to pick an action. But now, using the synchronization step, Lee et al. Is saying that that they will evaluate the advisors through the RL policy now. So this is just like shifting the problem. It's just shifting the problem from using the RL policy to pick an action. You're just saying that you don't want to use the RL policy to pick an action because your RL policy is next to random in the beginning of training. But I will use the RL policy to pick an advisor and use the advisor to pick an action. So this is just like moving the problem. It's not like solving the problem. So that is something that makes this algorithm, the empirical performance of this algorithm, be limited in many single agent as well as multi-agent contexts. And there is also a naive exploration among advisors, which is very limiting. So we inspire ourselves from this algorithm, and we introduce a new algorithm called multi-agent two-level Q learning in the general sim stochastic game framework, the same setting as what we had before. So now we apply this algorithm in the context of multiple agents and multiple advisors. So we have multiple agent, multiple advisor learning. And we provide an algorithm that has 4 important differences from the two-level Q learning algorithm from Lee et al. First of all, we have a multi-agent update where agents actively model the opponent as well. The second point is that the agents use policy reuse so that they guarantee no dependence on the advisor in the limit. So we have the same guarantee as before. There is no limitation on the advisor, so no dependence on the advisor in the limit. So agents can simply be deployed using their own policy. There is no more need for any advisor dependence. And we do away with the synchronization step. So the synchronization step is something that actually just shifted the problem, that didn't really solve the problem. So we do away with the synchronization step, and we learn. So we also have 2 Q tables, where the first table just evaluates the advisor, and the second Q table uses the advisor. So you can think of this algorithm as doing both ADMIRAL-DM and ADMIRAL-AE with the same algorithm. And then we have an ensemble selection method to select between an advisor. So the intuition is that at the beginning of training, when you know nothing about your advisor, probably choose an action where many advisors just agree upon. So if you have 5 advisors and let's say 3 advisors agree on one action and the 2 other advisors dissent, then probably that action is better. So use an ensemble selection method when you're not sure about the quality of your advisors. So we have an architecture which is very similar to what Lee et al. Had, but we do not have the synchronization step. But we have a multi-agent update, and the high-level Q table determines the value of an advisor, and the low-level Q table determines the value of an action at a particular state. So this is our contribution. So we have a set of theoretical results, same as what we had before. Let me just skip over that for the interest of time. And we have neural network implementations based on the advancements we see in DQN. I will show one particular result in this work in the 1 versus 1 Pomerman case, where we have we consider a series of opponents, like a series of baselines, learn from demonstration-based baselines like chat and DQFT, multi-agent model baselines like ADMIRAL-DM that we introduced before, no advisor baselines like DQN, and also two-level TAQL from D et al. And we show performance across a series of multi-agent environments, a series of contexts, like different types of advisors, different numbers of advisors, and so on. And in the vast majority of the cases, we show that the multi-agent two-level Q-learning method that we introduce provides the best performances. And it outperforms advisors as well as baselines after sufficient training in both training as well as testing execution style experimentation that we did before. So we have other results on several other domains. So with that, let me conclude. So if you, overall, to summarize, if you want a principal framework that can learn from single or multiple advisors in multi-agent reinforcement learning, that can work in non-restrictive multi-agent environments with suboptimal advisors, where advisors provide conflicting advice with strong theoretical guarantees, then check out our work. So yeah, some important links here, and I will stop there and I'm happy to take questions. Thank you.
All right, thank you, Sriram. Super interesting, and yeah, it's. I mean, I'm happy to see that a lot of this stuff works. Yeah, the conflicting advice and stuff. Yeah, if I were to think in like real life, yeah, I can't really ignore my advisors, but okay, let's take that as
well, it's always your choice. Yeah, so that's
yeah.
the beauty of this particular work, is that it's always your choice. The agents have a choice. They can choose to rely on the advisor or listen to their own policy, listen to their own, like, use their own Q values to pick an action.